Hello everyone, today I'll be doing a video on how to draw bode plots. And in this video, we'll use one of the tutorial problems as a guide. To start our discussion, we'll look at the following table. Basically, this table provides us a guide on how we can draw bode plots. If you'd be able to use this table, then you should be able to draw any bode plot diagram of any transfer function. In the tutorial problem, we've been provided with the following transfer function. So I'll demonstrate on how we use that table to draw our bode plot. Here in this table, we've been provided factors. So whenever we're given a transfer function, we would try to represent the transfer function in terms of these factors, because if we would represent them, the transfer function in terms of these factors, then we would divide the transfer function into sub-transfer function, if you allow me to use that. And then with that, you should be able to, for instance, if we divide the transfer function into these two, then we know that we can draw the sub-transfer function of this as this in the magnitude, the sub-transfer function of this, and this would be the magnitude. So as a demonstration, we look at this. We're given this transfer function, and then we want to represent it in terms of these factors. So this is for the numerator, this is for the denominator, this is for the numerator, this is for the denominator. As we all know that the JW represents an S, so we'll look at this. What I did, I factored out the 10, right? And then this is the term. And then here at the bottom, I factored out the 20, and then I had this, right? And then I left this as it is, and I simplified. After simplifying, we see that we have this, right, being the first transfer function. And you need to remember what it is. It's in the numerator. And then we have this 1 over 1 plus s over 20 as the second transfer function. We have the 1 over s as the third transfer function. And then we'll have this half as a fourth transfer function. Now the question is, how do we draw it? We look at this, we go to, this is 1 plus s over 10. And remember that s is JW. So we'll go to our bode plot table. This value is in the numerator, right? So we have 1 plus s over z, 1 plus s over 10, right? So our z is 10. It tells us here, if we're drawing the bode plot for the magnitude, this will run from 0 to a value of z, and it will increase at a slope of 20 decibels per decade. So this is transfer function 1. It's represented by this line h. So let's quickly draw it then. It tells us it will go from 0, right? From 0 to the value z, but here our value of z is 10. So it's run from 0 till 10. This is 10 to the 1. And then again, it increases at a slope of 20 dB per decade. This is a decade. So magnitude of 20 per decade. So I just went to 20, drew a point, and then connected, and that was my slope for accuracy, if needs be. But you could literally just indicate that this is just 20 decibels per decade, so that you won't have to, if you don't want to indicate a perfect value. So it runs from 0 to a value of z, which is 10, increases at 20 decibels per decade. So we go to our second subtransfer function. It's 1 over 1 plus s over a value. So we're looking for that here. So we have 1 over 1 plus s over a value. It tells us that it will go from 0 till p, and then it decreases at a slope of negative 20 decibels per decade. So we go here. This is the second transfer function, right? So we said it's going to go from 0 till 20, right? And it's going to decrease at negative 20 decibels per decade, right? So that was quite straightforward. So we just had to draw 0, 20, and then negative 20 decibels per decade. So we go to the third transfer function. And this S is on the denominator. So 1 over JW is an S, so it's 1 over S. So it tells us that if we're drawing this transfer function, we need to draw a line with a slope of negative 20 decibels per decade passing at 1. So we do exactly that. We're looking at this transfer function here. As we can see, it passes at 10 to the 0 at a slope of negative 20 decibels per decade, right? So that was straightforward. And then we go to the last one. This transfer function is a constant. So we'll go to our table as well. We see here a constant. You just say 20 log the constant, and then 20 log a half is just negative 6.02. So here it is, and it's a constant. It runs throughout, and it has a slope of 0. So we have drawn all our subtransfer function, but we want to draw how the final transfer function will look like, because remember, this represents the subtransfer function, if you allow me to use that term. So here we see that this is the final transfer function. But now how do we draw it? For me, the easiest way to do it is to look at the breakpoints of all subtransfer functions. Here it is, we have this breakpoint. Here for H1, it breaks at 10. And then we have, for H2, it breaks at 20. So here, these are the only breakpoints we have. So I just draw a line here to just show where the breakpoints are. And then after indicating where the breakpoints are, we divide this into regions. So we have region 1 from this point to where the breakpoint is, this point till there, and then from this point till here. So we look at this region first, right? We look at this region. So we want to draw the final transfer function. So basically, when drawing the final transfer function, is just the addition of all other transfer functions. So for instance, here in this region, we have this transfer function of H1, which is just 0. It has no impact. We have this transfer function of H3, and it's running at slope negative 20 decibels per decade, and it passes at 20. So now we're going to add, we're going to start here and add. So literally what you're doing, you're adding at every point, and then you are adding all the subtransfer function. But to start off, we'll say, okay, we have this transfer function of H4, which is negative 6.02, and then we add this transfer function here, it's 0. We add 20. So if you add minus 6 of transfer function H4, add 0 of transfer function H1, and then add 20. So these are the only transfer functions that are here, because yeah, and also add 0 for transfer function H3. So we have H3. It's sorry. We add minus 6.02 for this transfer function, right? This is transfer function H4. We add 0 for transfer function H1, right? And then we add 20 for transfer function H3. And then to sum up, we'll have a value of minus 13.98. So that's where it is. So now we're looking at this region, remember. So we're adding the transfer function. So to make it easy, what I do in between the regions, you just add the slopes, because here we just have, this is at a slope of 0. So now what we'll do is we'll add the slopes of each of the subtransfer functions. So here, this is minus 20 decibels, so minus 20, and here, H4 at a slope of 0 plus 0, and so we have H4, H3, right? And then H1, also here, it has a slope of 0. So it's basically minus 20 plus 0 plus 0. And then that's minus 20. So from that value, this will run at minus 20 if you add the slopes of this region at minus 20 till this point. But when you get to this region, we have minus 20 of H3. So minus 20, right? Plus the slope of this is 0 of H4 plus 0. Here, the slope of H1 is 20. So minus 20 plus 0 plus 20, it's 0. So that's why this is a straight line. And then we go to this region. So in this region, we have a value of positive 20 for the slope, minus 20, right, and minus 20. So in total, we have a slope of negative 20. So this continues at negative 20. That's why you notice that this is basically parallel to that. So if you look at the memo that the lecturer or the demis have made, you'll see basically it's the final transfer function here, it's the dark line. And you basically see here there are 14. As you can see, this is negative 20. And then we have this value here, which was a constant, and then at negative 20, which is the same thing as here. We have this negative 20 straight line and then negative 20. So that's it for the video.